my name is Gilliot. And these are the questions that I had for the short answer portion of the genetics exam, part 1. I'm going to go through how I got some of my answers and give you an explanation of how I did everything. So hopefully you can read everything on the board. There's a slight glare up here. And I wrote in red ink to start off with. The first question, it's asking about some observed ratios, and I wrote them here on the board: 222, 14, 20, and 64. And it's asking about, as the question says, with these phenotypic ratios, with the observed side, they ask us to propose a null hypothesis, create a chi-square value, and interpret the chi-square value, and whether we should reject or accept the null hypothesis. So just focusing on this portion right here, I went ahead and set up a chi-squared kind of diagram that I'm going to use to show you how I did it. First, I created a null hypothesis. My null hypothesis is that it would follow Mendelian inheritance. And so we'll find out. So what I did is I took the total, which is going to be 360, and you get that number just by totaling up all of these observed plants that were created. And so you take 360, and the guess is that if it's Mendelian genetics, the null hypothesis says that it's going to be at a 9 to 3 to 3:1 ratio. So the expected, if you even it out, 360 at a 9 to 3 to 3:1 ratio, it's going to be 202.5, 67.5, 67.5, and 22.5. And this is what you'd expect if it was Mendelian genetics and it was at a 9 to 3 to 3:1 ratio. And so what next you would do is you would find the observed minus the expected, this number minus this number, and then you just square the total. And so I calculated that out. It was 380.25. I might have done a little bit of rounding there. 2,862.25, 2,256.25, and 1,722.25. Then what I did next is I divided these numbers by the expected amount, and went ahead and did that, and that's 1.87 repeating. That was 42.403, 33.425, and 76.54. This gives you your chi-squared value by adding this number and this number and this number, and you end up getting 154.25. And so this is the number that I got. Then you use this table here. You're going to find the degrees of freedom, which is how many which for us is going to be 4 because we had, or sorry, which for us is going to be 3 because we had 4 different observed and expected values, 4 different kinds, and we just subtract 1. And so using that chart, we ended up finding out that this is going to mean that our null hypothesis is rejected. Because our null hypothesis is rejected, that means that this is not Mendelian genetics. It means that my new hypothesis would be that it's caused by environmental factors. So this is the first question. The second question on the short answer portion was asking about probabilities. So the first one, it was asking about go ahead and erase this. First question was asking about some parents that had children, and there's an allele that's there, Huntington's disease. This is the cross that was made, big D, and little d, little d. And so that would put you at like this, which would mean that half have Huntington's disease and half don't. And so because of that, the first question asks about the probability that all 6 of the children will be affected by Huntington's disease. So it's 1, 2, 3, 4, 5, 6. Well, if all 6 are affected by Huntington's disease, there's a half chance for each one, because it's 50% chance that they will get Huntington's disease. And so you just take this number, half times half times half times half, or you could just do half to the 6th power. And you're going to end up getting 1 out of every 60, or there's a probability of 1 in 64 that all 6 of their children would be affected with Huntington's disease. So that's how we did that one. Next one was asking about the probability that 4 children will be affected and 2 will be unaffected with Huntington's disease. So this is kind of a ratio. I went ahead and drew out the equation because we're going to use binomial expansion. This is the equation here. And so we have 6 total. And I'm just taking this equation. This is supposed to be an explanation. 6 total. And you're just going to plug in the numbers there. 4 is the number of children that will be unaffected. And then you're going to take total number, which is 6, minus the ones that are going to be unaffected. So that's going to end up being 2. Put another factorial. And p to the x, that's going to be 1/2 to the 4th, because 4 is our x value. Q 2, because that's n minus h. N minus h was 2 here, it's still 2 there. And you're going to end up getting from that about 23.4%. So that is the chance that you would have 2 affected with Huntington's disease and 4 that are unaffected. And so that's how I got that answer right there. And the last question was asking about the probability that the first 3 would be either all affected with Huntington's or all unaffected. So using kind of the same way that I did the first one, there's 3 kids, 3 children, 1, 2, 3. And use a different marker. I don't know if you can see it that well with the glare. 1, 2, 3. I think that's a little better. So you have 3 kids. And so 1/2 times 1/2 times 1/2, that's going to be 1 out of 8. And so that's the probability that all will be affected, is 1/8. Also, 1/2 times 1/2 times 1/2 is also the probability that all will be unaffected. And so it's asking how many will be affected or unaffected, which means that you add the 2 of these together and you're going to get 2 out of 8 or 1 out of 4. So that's the answer to that one. All right, now the next question, question 3. It takes us to some modes of inheritance. I'll just hold this up so you can be able to see it as I explain. So the first question here, it is showing us this one here, right here. This is the pedigree chart. And so what I found was that it's X-linked dominant, and as it says there, all daughters of affected fathers are affected and it does not skip generations. Skip generations means if somebody has it, you know, here, I'll show you an example of one that does skip generations. Here, you'll have a generation where somebody has it, then the third generation, nobody has it, the fourth generation, somebody has it again. So as you see, it doesn't skip generations, so it's dominant, and all affected fathers fathers are also affected. So that means that it's X-linked dominant. Next one, autosomal dominant. I found that out because it doesn't skip generations, much like the other one before it. And you kind of look at this little guy here that I circled. If it was X-linked dominant, then he would not be affected because he's not getting his X chromosome from his dad, he's getting it from his mom. And if his mom were affected, then he'd be affected, or he could be affected. But since his dad is affected, he's not getting that X chromosome from his dad if it's X-linked. So he can't be affected because of X-linked. It has to be autosomal. This one here, it skips generations, so it's recessive. And it's X-linked because more guys are affected than girls. And that's usually the trend that goes with X-linked. So the next one is X-linked dominant, this one at the bottom. And we know that because it does not skip generations, and all daughters of affected fathers are also affected, kind of like this first one here. So that's how I got the answers for that one. Number 4. Question 4 was asking about some African hedgehogs. And the chromosomes that they have is a diploid number of 90. And so it's asking about some different stages in meiosis and during a diploid, or during a cell's life, and like the kind of like the amount of things that it has, like chromosomes. And so the first one is asking about a set of chromosomes, the number of chromosomes that are present in each somatic cell of an organism. The answer I got is 45 pairs of chromosomes, because that would be a total of 90 chromosomes. 45 pairs would mean 90 total. How many tetrads are found during prophase 1? So a tetrad is a chromosome and another chromosome here. And so a tetrad is like where there's two chromosomes kind of lined up like that. And so much like set of chromosomes, there's going to be 45 tetrads. Sister chromatids is number 3. How many sister chromatids are during metaphase 2? I got 60 sister chromatids, because in a cell, that cell is going to end up, there's going to be 2 sister cells, each one still going through meiosis. And if they had the diploid number of cells, then they would each have 180, because each chromosome is going to have a sister chromatid. So boom, boom. So if there's 90 chromosomes, there's 180 sister chromatids, but these have divided already. There's half the amount of chromosomes, so it's going to reduce. It's going to be 90, sorry, well, not 19, 90 in each, because they've divided, and so they're going to have half the amount of data, genetic data that they would have normally. The last one for this question is asking about the number of chromosomes that are found during prophase 2. And for this one, I kind of follow the same 1B as before. Just dividing the amount of chromosomes, and it turns out to be 45. So question 5 then was, I went ahead and set up some of my data, how I got it here, but it's asking about a cross of well, I'll go ahead and write it. The cross is T, R, Y, other is T R R Y Y A. Okay, so this is the how do I say it? This is the cross here. One of these is the mother, one of them is the father. And you just cross these, and I end up getting these are the ratios for the offspring. There's a 1/4 chance of getting TT or homozygous dominant T. There's a 1/4 chance of them getting homozygous R, capital RT, and it just goes on like that as the data shows. And so the first one is asking, what is the probability of a dwarf? And that's going to be both little t's. Wrinkled, which is little r, terminal, which, let's see, terminal, what does it say here? It's this one, little a, and yellow, which is big Y, little y. What's the chance of these? So you end up multiplying this across 1/4 times 1/4 times 1/2 times 1/2, and you end up getting 1 out of 64, and that is the chance of you getting those phenotypes. All right, so the next question was asking about, let me see here. It was asking about the probability that an offspring plant has big T, little t, so this one here, big R, little r, this one here, big Y, little y, this one there, and big A, little a, which is this one there. So just like the one before, you just multiply them across, so this times this, that times that, and you end up getting 1 out of 16 this time. You could also just say, all these are 1/2. 2 out of 4 is 1/2. So you could just do 1/2 to the 4th, and you're going to end up getting the same answer. All right, so now the next one. All right, so the next one is saying, what is the probability of the first 5 offspring having big T, this one here, little r, this one there, heterozygous, that one, and little a there. And once again, you just multiply them across, and this is going to end up being, it's asking about the first 5 offspring. So you multiply them across, and you end up getting 1 out of 64. This is for one offspring. If you just wanted one offspring, you wanted to know the chance you get 1 out of 64, but you don't want to know the first offspring. You want to know the first 5 offspring. If you had 5 in a row, back to back, what you would have to do then is take 1 out of 64, which is the chance of it happening once, and times that by itself 5 times. And you would end up getting 9 point, and this is rounding a little bit, but it's 9.31 times 10 to the -10, which is a super small number, but that is the chance, the probability of the first 5 offspring having these genes. All right, so the last one is asking about the probability. Let me erase some of these circles. Good. So the last question is asking, what's the probability of an offspring plant having dwarf round yellow and axial phenotype, or dwarf wrinkled green and terminal? So the first thing you're going to want to do is to figure out what is the probability of having dwarf round yellow and axial. So dwarf is going to be this one here. And round is going to be, let's see, round is anything with the dominant gene. It's going to be those. Yellow, this one. And axial. Axial means big A. So right there. So you end up multiplying these across, and you're going to get 3 out of 64. You're not done there. You got to find out what the second The second probability is, which is dwarf, which is still that one. Wrinkled, which is the little one. Green, which is this one. And terminal, which is that one. And so you end up multiplying those across, and you're going to get 1 out of 64. And the question isn't asking about this alone. It's asking what is the probability that you could have this or this. And so you're going to end up getting 4 out of 64, or that's the same as 1 out of 16. So that's your answer there. It's the same as 6.25%. So that's how I got my answers. Hopefully that was pretty easy to follow. And I hope that everything made sense to you. Hopefully this video sounded good and you can see the board all right. But thank you guys for watching and have a great day.